Welcome to the Chemistry, Biology and Math Revision Hub. Today we'll be doing the January 2022 Chemistry Unit 4 Section A for Pearson Edexcel International A level. This part, of course, I'm going to do Section A first, which is 20 marks, and in the next video I'll be able to do the other section. So I'll begin from question 1, or with question 1. Question 1 says, a simplified Born-Haber cycle for the formation of lithium iodide is shown. So here, this is the cycle we're given. And then they say the enthalpy change of atomization of iodine, which is given here. Okay. Let me just position the pen back on here. And then, okay. So they say the enthalpy change of atomization of iodine, given to us as that, is given by the equation. So they want you to find the equation that is, of course, showing the enthalpy change of atomization of iodine. What we need to know is what enthalpy change of atomization means. It means when 1 mole of gaseous atom is formed from the element, basically. So it means the product should be 1 mole of a gas. Like this is a good example, that is a good example, that is not, and that is not. However, the reactant should also be an element. And we know iodine at room temperature, or at 298 Kelvin, iodine is going to be a solid and not a gas. So B comes out to be the best answer, which we should put here. The next question says, use the information in the cycle to calculate the electron affinity of iodine. So if we are looking for the electron affinity of iodine, we have to find a way of making this equation work. So I can make this the subject and then follow this pathway and that pathway, and then I can be able to later on make this the subject, which is going to be what I'm looking for. So I began by saying this, which is negative 270, is going to be equal to 107 plus 160 plus 520 plus the electron affinity plus the negative 759, and then I make the electron affinity the subject. So this is what I did here. That is equal to the others basically. And then in the end, I made this the subject, which comes out to be negative 298 kilojoules per mole, which is answer A. So I will go to the next part, which is question 2. Question 2 says, some energy changes are given in the table. So here we have some energy changes. We have the lattice enthalpy of calcium chloride, solid, the enthalpy change of solution of calcium chloride as well, and the enthalpy change of hydration of chloride. So they say, use the data to calculate the enthalpy change of hydration of a calcium 2+. What we need to know is if you're trying to calculate the enthalpy change of, in this case, it's hydration, we can use this formula that the enthalpy of solution should equal to the negative of the enthalpy, which is basically lattice enthalpy, plus the hydration enthalpy, basically, hydration enthalpy. And then we can substitute in the individuals, like in this case, in enthalpy of solution, of course, it's going to be for the whole calcium chloride, which is going to be negative 120, should equal to the lattice enthalpy, of course, which is for the solid as well, which is negative 202.58. However, this should be the negative of that, so the negative of that, and then plus hydration. Now, what we need to know is if you are trying to hydrolyze calcium chloride, you form a calcium ion and you form chloride ions. So in this case, the hydration is going to be broken down into 2. The first will be the hydration of calcium ions, which we are looking for. Let's call it DH, hydration of calcium 2+. And then the other is going to be the hydration of the chloride. However, we have 2 chlorides, so I say 2 times the hydration of chloride, which is going to be twice that, because this is for each chloride ion. Since calcium chloride has 2 chloride ions, we're going to multiply that by 2. So then, in the end, we're going to make this the subject. So you can see I substitute for that, and that, make this the subject, and find this as the answer. So the answer comes out to be B, which is negative 1,650 kilojoules per mole. So I will continue to the next part. So question 3 says, the reaction shown is at equilibrium and the forward reaction is endothermic. So if this is an equilibrium reaction and the forward reaction is endothermic, it means the backward reaction should have a negative enthalpy change, which is going to be exothermic, basically. Let me just exothermic. So the question goes on to say, which will increase when the temperature is lowered? One thing that we need to know is, if the forward reaction is endothermic, it will prefer increase in temperature. So if the temperature is lowered, it means the backward reaction is going to be favored. And when that backward reaction is favored, we're going to produce more carbon dioxide as well as the carbon. So they're asking which will increase when the temperature is lower. Lowering the temperature will lead to an increase in the mole, so of course increase in the mole fraction of carbon dioxide, because of course this is a gas, its mole fraction is going to increase. The partial pressure, no, all the other answers do not make sense except A, where we see they say the mole fraction will increase. So the rate, forward and back rate will increase. No, this is out and that is out. So the correct answer should be A for that part. And part B says, at 680 degrees Celsius and 1 atmosphere, 52.6% of the molecules in the gas mixture are carbon monoxide. What is the partial pressure of carbon dioxide in atmospheres? So based on this equation, you can see we have only two gases. Carbon dioxide is a gas and carbon monoxide is a gas. The calcium solid, the carbon, which is a solid, does not contribute to the gas, and therefore it does not contribute towards the total pressure. So if the partial pressure for carbon monoxide is 52.6, it means the partial pressure for carbon dioxide should be 47. It should be we can get it by using 47.4. So it's going to be 47.4%, and in this case 47.4% is going to be 0.474 atmospheres. And again, I'm going to affirm if this is the percentage, it's going to be 0.526. That is going to be the partial pressure of the carbon monoxide, meaning the carbon dioxide will retain the other fraction, which is 0.474. The answer will end up being C. Question 4 says the equation for the precipitation of lead to chloride is shown. Okay, and they ask what are the units of the equilibrium constant Kc. So what we need to know is if we are finding out the equilibrium constant for Kc, it's usually going to be Kc is equal to the concentration of products divided by the concentration of the reactants. Now in this case, products is going to be basically concentration of PbCl2 divided by the concentration of Pb2 plus, and then the concentration of Cl minus. Since this is 2 times, we put that to the power, so it's going to be squared. However, this is a solid, and therefore we do not consider the solid, so it comes out and I remain with a 1. The solid is not going to be considered, so now we remain with 1 over the concentration of lead 2 plus, concentration of chloride minus squared. And since each concentration is mole per decimeter cube, that part becomes, this part here is going to be that, which is mole per decimeter cubed, and the other part is going to be this, which is mole squared per decimeter power 6. When we combine the two, we get decimeter power 9 divided by mole cube, which comes out to be A as the answer here. So I'll continue to question 5. Question 5 says, an example of a diprotic acid is cis-butene dioic acid. Titration of this acid using sodium hydroxide solution gave the titration curve as we can see. So they're using sodium hydroxide solution, that's why the pH is increasing. So they say, which indicator would be most suitable for measuring the endpoint of neutralization of the proton in cis-butene dioic acid, which has pKa of 6.33. So here you have to refer to your data booklet, and when you look at the data booklet, since we are using sodium hydroxide, the pH is greatly going to increase, and in this case, phenolphthalein, which works best in the range of 8 to 11, which is basically within that vertical line, it's going to be a suitable indicator in this case in comparison to all the others. So phenolphthalein is suitable. You can refer to the data booklet to find the ranges through which the others work, but of course phenolphthalein will be the best candidate. Question 6 says, at 25 degrees Celsius, the pH of pure water is 7. This is a lower temperature is 7. And then at 100 degrees Celsius, the pH of pure water is 6.14. So we can see the higher the temperature, the lower the pH, or the higher the temperature, the higher the acidity. So that's what we get from that statement. And then they say, what can be deduced from this information? What we see is higher temperature, more hydrogen ions are going to be present in solution, meaning the water is going to be dissociating. So there is more dissociation, which increases with temperature. So what we can see here is the enthalpy change of dissociation, of course, is going to be endothermic because it requires heat. And then on the other side, the concentration of hydrogen ions are going to be higher at 100 degrees than at 25 degrees because, of course, there was the solution was more acidic at 100, meaning there were more hydrogen ions released in solution at 100 than those that were at 25 degrees. So let's continue on to question 7. Question 7. The anti-inflammatory drug ketoprofen has the structure shown below. The structure shown below, let me erase out what I wrote so that I can show you how the structure looked like previously. That is how the structure looked like. So I'm going to insert back what I wrote because I always advise students to draw in the carbons and hydrogens to avoid making mistakes. So the question says, what is the molecular formula of ketoprofen? We begin by counting the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 carbons. And then I'll go to the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And I'll go to the oxygens. 1, 2, and 3. So this gives us the molecular formula, which is C. Question 8 says, menthol has a number of medicinal uses. It can be extracted from the peppermint plant, and the structure of menthol is as below. So they say, how many chiral centers are there in one molecule of menthol? Chiral center has to be a carbon attached to 4 different groups. So this is not a chiral center because it has at least 2 groups that are similar. That is not. That is not. So if we roll out those, and that is not because, of course, it has three hydrogens. So rolling out those leaves us with only, also this one is not because it has this group similar to that. So it leaves only that carbon, and that carbon. So we have 3 chiral centers, and that is the answer to question 8. I will go to question 9. Question 9 says, which of these reactions does not result in formation of a racemate mixture? Remember, a racemate mixture is a mixture where we have 2 enantiomers that are in equal concentration, of course. So here, the first one is butane with HCl. When butane reacts with HCl, the structure of butane is like that. When it reacts with HCl, we form a product. However, this product goes through an intermediate, basically. The intermediate, so when we form the intermediate, we're going to have that. I can put a 2 here, and there is a carbon that will have a CH3 on the other side, and of course the hydrogen on it like that. It means this is planar in shape, and therefore the incoming nucleophile can attack from both sides, creating 2 possible enantiomers that are in equal concentration, and therefore a racemate mixture can be formed. So with A, there is possibility of formation of a racemate mixture. I will go to B. B is but1N. But1N can be drawn like that. Now, when but1N reacts with HCl, there are 2 possible products we can form. One is going to be through a primary carbocation, and one is going to be through a secondary carbocation. So I will draw the one with a primary carbocation. So it will be CH3, CH2, 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 Cl. Formation of this, because on this part here, formation of this basically will go through this intermediate, CH2, CH2, and then a C, a positive, and you have 2 hydrogens. So it means there is no possibility of formation of a racemate mixture since we have 2 hydrogens or 2 groups that are similar on the same carbon. The other product that could be formed through this mechanism is CH3, CH2. That is if it's the secondary carbocation, so CH plus, and then a CH3. With this one here, there is a possibility because this is going to be trigonal planar. Again, let me erase this product and transfer that to show you how it would be. So transferring this to that side, so it makes us have the intermediate would be like that. I'm trying to present it in a form that is more understandable. So the hydrogen there and the CH3 here, it means this is there is a possibility because of the shape, basically. The nucleophile that is coming in, meaning the chloride, can attack from either side, leading to the formation of 2 possible enantiomers that could be in equal concentrations. So we can say a racemate mixture can be formed. So that can form, that can form. Propanol can also form because, of course, propanol will form a structure that looks like that, and it's going to be in that form as well. And lastly, with propanon, even if it forms, if this is the central carbon, that group and that group are going to be the same, so there is no way a racement mixture is going to be formed because this is not a chiral center. It's not a chiral center. Center. And again, I want to separate this so that you cannot, it's not a chiral center. So the answer should be D. And for question 10, when a single enantiomer of 2-iodobutane reacts with sodium hydroxide, the product is a mixture of enantiomers. They say this is because the key part of this question is that they want the reason why the product is a mixture of two enantiomers. The reason for this is what I've been explaining above there. The reaction goes through a carbocation intermediate, and when a carbocation intermediate is formed, it means the incoming nucleophile can attack from either side, which leads to the formation of a mixture of enantiomers, basically. So question 11 says, how many structural isomers with the molecular formula this react with Tollen's reagent? One key thing is Tollen's reagent is ammoniacal silver nitrate. It contains silver in +1 oxidation state. When it reacts with aldehydes, a redox reaction takes place and the silver is converted into silver, which is a solid. And this is why we see the silver color, so the silver mirror. So it means if Tollen's reagent is reacting with something, that thing should be an aldehyde. And the 4 possible aldehydes I got were this, meaning this has only 4 aldehydes. So basically the answer for this is going to be, for question 11, is a C. Let's continue to question 12. Question 12, propanone reacts with iodine in both acidic and alkaline conditions. The product of this reaction under the stated conditions include as below. So here we know when it reacts with this and in the presence of iodine, it's the iodoform reaction, and the product here is going to be, we see triiodomethane basically. This is there to confuse and that, so those are out. So they ask the product of the reactions under stated conditions are, in acidic conditions, you have this reaction here. It's present in the unit 4 section of your textbook, and the product we see is actually that. And when it reacts in alkaline conditions, of course, we see the triiodomethane, so the answer should be D. The next part says, the rate equation for the reaction between propanone and iodine in acidic conditions is as below. So this is the rate equation, meaning that it's first order with respect to each of the components, and then they say the reaction was carried out at 2 different pH values, all other conditions remaining unchanged. And they ask, in the first reaction, the pH is 2. In the second reaction, the pH, the rate was found to be a third of the original. So if I can use the equation, if this is the rate equation we're talking about, and this is the old rate, and the new rate is basically a third the original rate. So if the new rate is going to be a third the original rate, yet they said here all the other components remain unchanged. So it means even the concentration of this remained unchanged. So it means it's only the concentration of iodine that changed. If the rate has increased but has changed to be a third the original rate, it means it's because the hydrogen ion concentration was a third actually since it's first order with respect to it. So assuming the new rate is equal to a third the old rate, it means it's going to be basically a third the original concentration of hydrogen ions. And since we know the old pH was equal to 2, as you can see here, the new pH is going to be, we can use the old pH to find the concentration of hydrogen ions. Again, you know, pH is equal to negative log over H plus. So we will say 2 is equal to negative log of H plus, and use that to find the hydrogen ion concentration, which comes out to be this, and that's the old hydrogen ion concentration. So the new hydrogen ion concentration is a third of that, and then we can say the new pH is negative log of the new hydrogen ion concentration, which gives us a pH of 2.747. However, they said it has to give your answer to 1 decimal place. Rounding off gives us the answer 2.5, and the answer here ends up being a C for question 12. So I will continue on to question 13. Question 13 says, but2-in 1,4-diol may be converted into 2-oxobutanoic acid in a 2-step synthesis through an intermediate compound W. So they say, identify the intermediate W and the reagent for step 2. So here I will use a different marker. So we know that this is here, there is an alkene as well as alcohols on the other side. When you use an acid and steam, this is water, introducing gaseous water, it means we are trying to hydrolyze. This is basically hydrolysis, and the alkene is going to be converted into an alcohol. So this part here, a hydrogen will come onto one of them. These two things here, one will gain a hydrogen and one will gain OH, meaning we get an alcohol on that side. And so W is going to look like this. And then the next step says, so this for W can be this, as you can see that. And then the next step they say, we formed a carboxylic acid. To convert this into a carboxylic acid, you can see this is a carboxylic acid, and this is a ketone area. So it means this ketone must have come from a secondary alcohol, and these carboxylic ends could have come from a primary alcohol. So it means this was an oxidizing agent. And the suitable oxidizing agent could be, of course, acidified potassium dichromate. So you can see this could be that or that, and here we can see there is only one oxidizing agent, so it makes D the answer because it fits the two conclusions we have seen here. For question 14, they say compound X. We have compound X as that is oxidized to form compound Y. So we are not sure if X is an alcohol or an aldehyde, just leave it like that. And then they say compound Y reacts with ethanol in the presence of sulfuric acid to form an ester. We know, I'm going to break it down here. If Y reacts with ethanol to form an ester, then Y is a carboxylic acid. Okay? Because only carboxylic acids and alcohols will form esters, or at least in this case. Or it could be, of course, an acyl chloride in the other, but this is a different situation. Now, if Y is a carboxylic acid and it was formed through oxidation, it must have been either a primary alcohol or it could have been an aldehyde. However, here they said we have the compound X. So compound X is oxidized to form compound Y, and then it reacts with ethanol. So it could be any of this. So if they want us to find out Z, which is the ester formed, remember esters are formed when the one part comes from the alcohol and the other part comes from probably the carboxylic acid. So they say, which of these could be ester Z? Ester Z can never have a group like if let's assume this is CH3, C, O, and then the other group. This group can never be, it can never be secondary, it can never be tertiary, and it can never be secondary. It should be only a possibility. In this case, this is going to be ethanol. But the part that was oxidized, this part here, it could never have been a secondary alcohol, and it could never have been a primary alcohol, a tertiary alcohol. It should be primary alcohol only, like I concluded here. So the alcohol should have been primary. And when we look at this part here, you can see here it shows there was a primary alcohol, as you can see here, because actually in this case here, when you see this is be a primary alcohol, because as you can see here, although these groups are branched, the alcohol should have been primary, and this is the only part that comes from ethanol. So that is the only part we have here. So the answer, a suitable answer here should be C, because if you break down everything, you get 14 here. Question 15. Which of these compounds is a product of hydrolysis of this by refluxing with aqueous sodium hydroxide? So if we are talking about hydrolysis of an ester, when you use sodium hydroxide, that is alkaline hydrolysis, and we know when you carry out alkaline hydrolysis of an ester, you form a carboxylic salt as well as an alcohol. So we have to make sure the alcohol formed is going to be, of course we break it from here. That part forms the alcohol, and this part is going to form the carboxylic salt. So the possible carboxylic salt should be that attached to sodium, because you use sodium hydroxide, and the possible alcohol part should be carbon 3, hydrogen 7, or H. So these are the two possible things that we should see. So here they're asking which of the compounds is a product. Of course, it could be that or that, and the only answer available here is, of course, this alcohol, because the others are different, so the answer should be B. This is alkaline hydrolysis. Question 16 says, in gas chromatography, a gas containing a mixture is passed over a liquid, stationary phase. So the stationary phase is a liquid. And they ask, the main reason a mixture is separated into its components is because of the different the components that are being separated are going to interact with both the mobile phase and the stationary phase. So the interaction with the stationary phase allows the components to be separated so that the mobile phase carries different components at a time, so that their retention times, or basically their retention times, are going to be varied depending on their interaction with the stationary phase. So here again, they've told us passed over a liquid stationary phase. So the separation is due to the interaction with the liquid, which is the stationary phase. That interaction with the liquid allows these components to be separated and therefore moved through the chromatography, the gas chromatograph, at different rates in order for them to be separated properly. So the answer should be B. Question 17, they say in HPLC, the mobile and stationary phases are. Of course, HPLC is a higher performance liquid chromatography. You're going to have a mobile liquid that is pushed at high pressure, and then a stationary phase that is going to be a solid. So the answer here should be D. The mobile phase is the liquid and the stationary phase is a solid. This brings us to the end of the section A of this paper. This is Unit 4, January 2022. Thank you for being with us, and we look forward to seeing you in our next video when we discuss section B as well as the other parts of the paper. So please do subscribe to our channel, and we hope to see you next time. Thank you. Bye-bye.